Alrighty, welcome back. Continuing on with addition rules for probability, if you're privy to the conversation that I just had. Of course, we may or may not have class on Tuesday. I will keep you posted. You're going to want to keep up with your announcements. So basically, if you hear from me, I will send an announcement if I'll be here on Tuesday or not. Okay, regardless, no matter what, I will let you know whether we're having class or not. Now, remember, there is no school at the JC anyway. There's no school here on Monday because it's President's Day. Okay. Just kind of a heads up what's coming today. I'm gonna get through 4.2 and I'm gonna try to go ahead. Better taking sorry, right? Let's go ahead and get through 4.3. Next week when we come back, we'll get through 4.4. We'll do that on Thursday. 4.5, you're gonna realize that I don't have any videos for that and I probably won't put any. 4.5 is just a combination of everything from 4.1 with 4.4 added to it. And so it's about like, I think 6 or 7 questions on your homework. They're good to go over. I've got a few notes in there on how to do some of them, just to kind of like look at them. But it is good to kind of work through them just because, excuse me, they will be, I pull one of those questions for your midterm. Okay, so just kind of have a heads up for that. Okay. So like I said, jumping back in, I'm gonna just kind of go through pretty quickly and then I'll get up to where we supposedly stopped. If I'm wrong, blame her right here. She's looking right there, raise your hand. No, but I'll kind of just kind of go through so we kind of get through this. It was a very quick class, the last one, because of the test. So remember addition rules of probability. Okay, a few rules about probability we need to remember. You cannot have a probability less than 0 and greater than 1. The sample space, if you add up everything, all your outcomes total in the sample space, it's always going to equal to 1. And then if you have something that's sort of like what that last term is saying is if you have something that's just impossible to happen, like say rolling a dice that's greater than 6, that's impossible. That's what that last term is saying. Really, that's the mathy way of saying that can't happen. Okay. So there's kind of that right there. It kind of helps for some conceptual understanding. Like I said in the last class, if someone says, man, there's a 120% chance that's going to happen. Well, that person doesn't know what they're talking about. Okay. You can't have 120% chance of probability. Okay. 120%, that's finances, not probabilities. Okay. Remember, we talked about complement, not complement. Okay. Complement, okay, of an event. Literally, it's just the opposite of that thing happening. Okay. So if I have, like, say, a 1 in 6 chance of rolling a 5, okay. Well, remember, the complement would be a 5 out of 6 because it's the chances of not getting a 5. It's always the opposite side of that coin. Okay. Can I help you out on that? And the reason we do it, 1, so you have an understanding of it now. 2, it will come in very useful later when we start doing normal distributions and especially on your calculator. Sometimes when your calculator saying, hey, just do this and this and this, we can take those 3 steps and make them into 1 step by just knowing the complement. Okay. Kind of makes it a little easier. I'll let you know about that later on. But I kind of want you to keep up with that vocabulary of it. Sort of like how we've been doing with the Greek and everything else. So there we go. There's just kind of example. Notice you have a sample space. That's what it was talking about when it said, hey, the sample space is always equal to 1 because it's everything. Okay. Think of it like your universe. What's in my universe? Everything. Okay. And then we start narrowing our universe whenever we start thinking about the frequency of the thing we're looking for. Okay. Be it good or bad. Like I said, sum of all these events, when you take the sum of the event and then the sum of the complement, it equals 1. Makes sense when you really think about it that way. Okay. What is the probability of rolling a standard 6-sided die? Remember this one? I did this one. Like I said, I'm not going to show you the notes. The video will be posted this week. Week 4 videos are up. So in case you need to go back and do some review. Remember this one because there was going to be a lot of ways. Okay. When we did the math of this, there was 25 out of 36 ways not, okay, to get a 3. But notice there was a lot less ways to show how to get the 3. So sometimes it's easier to go ahead and find the complement and then reverse engineer it, minus it from 1 to get what we're looking for, okay? So sometimes it's easier going that direction. Then you have this. For two events, E and F, the probability that E or F occurs. Now, I don't know if I mentioned this in the last class, but I don't mind mentioning it again. How do you know you're gonna be dealing with an addition rule? If you see it on your midterm or anything like that? Yeah, that guy right there. Look for the or statement, okay? They're gonna say, I need the probability of this or this, okay? Remember, that's an inclusive or. In math, we use inclusive or. That means this or this, we put them together, not this or this, okay? Notice that last section there, that and, okay, right here, that's going to be our intersection. So if you go back in time and remember sets, or was a union and was an intersection. You can see that very easily by looking at my little Venn diagram here. Okay. You remember doing the math of this one, how I said, hey, so many students at this college were freshmen, so many were math majors, I think it was like 3%, but then there was an intersection of them. Right here, and it was like 0.5% was the intersection. Well, with this, is it possible that someone could be a math major and also be a freshman? Yeah, so there is somewhere in there that somebody could be counted twice and we need to remove them from that, okay? And so that's how come we have this formula here. It's the removing of something. Kind of makes sense, right? All right. Then I think we did this one right here. I think this is probably where we ended, okay? So notice, okay, on this one, when we did it the other day in class, it says, hey, this person, they're looking for something, okay, they're looking for a condo, and read the question at the bottom. What is the probability that the property is either close to the subway, and there's our word we're looking for, the or statement, which says I'm gonna have to take two things and put them together, okay? Well, it says the probability is either close to the subway. Well, that could be it right here. Close to the subway, that could be my probability of E, or however you want to write it. And then it also needs to have a low maintenance fee. Well, that's nice. That could be my probability of F. Now, if you're not careful on this one, or one like this you might see in Hawks or something like that, realize, look what they do in here. There is an intersection. There is a few apartments that count as both of them. And so think about it. This right here, we could count that as my probability of E and F. So when we do the math of this, okay, notice they give us all the outcomes. There's 17 possible condos we could be looking for here. Okay, so thinking of our formula, the probability of E or F is the probability of E plus the probability of F minus the intersection. Where do they match? Okay, so minus the probability of E and F. Do our math very quickly here. Notice we've got 6/17 plus, what we got here? 7/17 minus, notice here that 2/17. Okay, so when we finish all that up, what do we get? What's that? 6 plus 7, 6 plus 7 is what?
13,
Minus 2.
11.
Very good. Get 11/17, which is a valid answer. Okay. Or if you're worried about getting, remember, if you're worried about getting really large fractions, which you will, you're going to get some pretty large fractions at times. Nothing's more annoying than that blue bar that happens in your homework. Okay. So I would suggest go ahead and just do the division on this and turn it into a decimal. And remember, what I saw a lot of on your test that I was go back and grading, just the rounding. A lot of it was rounding, okay? Like on one of them, the answer was 0.67. Up here, we're putting like 0.666667, okay? Round to two decimal places, okay? And just a little word to the wise. Put the 0 up front, okay? Put 0 point, okay? Show that front 0, okay? I go in and grade. If you don't start showing that front zero and it says, don't worry, you didn't get it wrong. I went back in there and counted right. Okay, so don't worry about that. How, my test would have counted wrong. I went back and fixed it. You'll get your answers, at midnight tonight. Okay? So, but notice on this one, if you do the math to this one, you're gonna be able to get 0.6471. So. We're good on that. I think that's about where we made it to, okay? And then we'll kind of start from here. Can you see how some things can happen together? More like those things, they weren't working independently of each other. You could go get a condo that literally it said it could be close to the subway, it could have low maintenance fee, but then there was two that fit both criteria. Okay? That means those events were not mutually exclusive. Okay? So what is mutually exclusive? Notice I'm giving you a different formula here. It looks exactly the same. We are still using the probability of P or F. Okay? But now it's just the probability of E plus the probability of F. I've gotten rid of the intersection because some probabilities, okay, some things can only happen in one way. There's no shared events. Think of it this way. If I roll a dice, is there a way for me to get a 2 and a 5? That makes no sense, right? Okay, if I flip a coin, I can't get heads and tails at the same time. Those two events are mutually exclusive. So they're never going to have anywhere where they match up, where you have to kind of take out that intersection. It's kind of nice when that happens, okay? Hardest part about some of this is sometimes figuring, which is why in some of your Hawks problems, it asks you, is this event mutually exclusive? Okay, that kind of help you out a little bit. Sometimes that's hard. So, think flipping coins, rolling dice, okay? Even, okay, when you get into a more like real world example, what if I was studying the probability of someone having a disease? Wouldn't that be a mutually exclusive event? I've either got the disease or what?
You don't go.
I don't. You're either sick or you're well, okay? You're dead or you're alive. You can't be alive and dead at the same time, okay? That's a mutually exclusive event. It may be able to be sunny and raining because we live in West Texas and Southern New Mexico, but it can't be rainy and dry, okay? Mutually exclusive events, okay? Look at this example here. We're going to roll a pair of dice. What is the probability of rolling either, okay, a total less than 4, or there's our operative word I want you to start getting used to seeing when you know you're dealing with a probability problem, okay? How do you know you're dealing with a probability problem? Well, probably because I'm going to say the word probability to you. Okay, this is going to help you out on a midterm, okay? Of either rolling a total less than 4 or a total equal to 10. Now, before I even show you, does that sound mutually exclusive? Can you have a total of 4 and a total of 10? No, you're either going to get the 4 or you're going to get the 10. You can't have both, okay? Since these are mutually exclusive events, there's nowhere in there that I need to get rid of an intersection. Let me show you what the dice look like. There. There's my totals less than 4, and there's my totals to 10. Now, just in case someone in here is seeing something and they're like, wait, hold on. How come that works? Look at the 4. One thing that should be noted. Notice how these are basically the same dice, okay? Except look at them. This right here was my first dice. So there's a probability of getting a 1 for that one, right? And then over here on my second dice, there's the 2. Okay, but then on the second dice, look, the second roll, the first dice I got was a 2. The second dice I got a 1. When you're counting these probabilities of dice, you have to count both ways, okay? Because there's 2 ways to get to less than 3 on this, or less than 4, right? My first dice could be a 1, my second dice is a 2, but then we can flip those. The first roll could be a 2, the second roll could be a 1. You gotta think of those two dice as two separate things that could happen, okay? And then notice we got the 10. So obviously, as you can tell, do you remember how many outcomes are possible for a rolling of dice?
36.
36, exactly. There's 36 possible outcomes. I have 6 possible ways of getting something on this dice, right? I have 6 possible ways of getting something on this dice. When I multiply those together, which you'll see about that rule here in the next chapter, you'll see how I got the 36 or 6 squared. Okay, but if you think back to your coin example, remember, hey, whatever, how many ways could I get a heads or tails? 2. Well, if I rolled again, remember that went to a 4. Rolled again, that went to, it was just 2 times 2 times 2. Okay. Notice here, we do the math of this. Notice since they're mutually exclusive events, what is this probability right here? What would be that? That's going to be the intersection of them. How about 0? Do you see where there's any way that I could have something? First off, just look at the picture. Do you see any dice that match on either side? Doesn't have, so they're mutually exclusive events. So that guy literally right there is just a 0. And then we can just come in here and go, well, how about less than 4? How about 3 out of 36? Plus, how about 10? I've got 1, 2, 3, another 3 out of 36. And here's a little word to the wise. Don't simplify until you're completely done. Okay? Keep all the outcomes. Like right now, you know, you could take that and go ahead and since they match in the numerator and denominator, it would be okay. Don't do that. Okay, this is a rare occasion that that happens. Don't simplify until you're at you've got your answer before you decide to simplify. Okay, this isn't like college algebra where we said, hey, simplify then multiply. No, simplify at the very, very end. Okay. Come in here, notice when you get this all done, you get 6 out of 36, which is just going to equal to 1 over 6, which is just going to end. Put a little squiggly line there. 0.1667. Remember, whenever you're doing your probabilities, when rounding for probabilities, you want to write this down, round to 4 decimal places. That's a rule. Okay. It is the rounding rule for probabilities. Remember to round to the 4th decimal place, we look at the 5th number to decide what we're going to do with the 4th number. Okay. Good so far. Not lost. Probably gonna take some practice a little bit though, just kind of get used to it. Yeah. Caleb is very excited that it's finally time to purchase his first new car. After much thought, he's narrowed his choices down to 4. But it's taken him so long to make up his mind, his friends have started to bet on which car he will choose. They've given each car a probability based on how likely they think Caleb is to choose that car. Devin is betting that Caleb will choose either the Toyota or, there's my word, the Jeep. Find the probability that Devin is right. Now, before I get going, it's always good to take the time to review. Would this be a subjective probability, classical probability, or an experimental probability? Why subjective? Their opinion. Now, would you say it's probably an educated guess? If they're good enough friends, yeah. Okay, like my wife's gonna understand what type of car I like. Okay. So she might be telling like her sister, like, I think he's probably gonna get this one because I know him. It's not 100% right because I am kind of wild sometimes and pick something way different. She knows I'm gonna stay within a budget. But now here's another question. Is this a mutually exclusive event? It's not. I have not, I have yes. Well, for it not to be a mutually exclusive event, what has to happen? For it to be, okay, for it not to be a mutually exclusive event, what would have to happen? You have to get two cars. Can you go and buy two cars? Probably not. We hear people doing that, like maybe, on the TV, but do you really know anybody that went out and bought two cars? Okay, a husband might go buy, or a wife might go buy two cars, her and him, right? But I don't think I've ever heard of any man or woman and just said, I can't decide on which car I want, so I'm gonna buy both of them for me. No, they end up just usually buying one. Okay, so no, this would be a mutually exclusive event. There's nowhere there's gonna be any sort of intersection, okay? So notice, we don't have to worry about subtracting something off. We just gotta add those probabilities together, okay? So we know he's looking at either the Toyota or means I'm adding it or adding it. So I just literally come here, the probability of him getting a Toyota, spell that right, or Jeep. Notice how when you're doing these probabilities, yes, it is A-okay to write a sentence on the inside. That's just going to be, how about 0.40 plus, and the Jeep is going to be 0.35. Well, how about 0. What?
75.
Very good. 0.75, or hey, I don't know about you, but I don't think I'd want to take this bet against Devin. Okay, I take that back. It depends upon the amount of money we're talking. We're talking about $5, I might take the bet. We're talking $100, I ain't taking this bet. Because Devin may be the better of the friends and he knows Caleb a lot better than I do. Okay? Because there's a 75% chance, that Caleb's right. Or sorry, that Devin is right. But here's the thing, remember, this is still subjective. Caleb might have no clue. He might be the new friend who's just kind of overbetting. Okay, so kind of a good way to think of it. We will be learning about expectation and risk, so that'll be kind of, to me, that's fun. I know I'm a nerd. But it is fun to you can actually go in there and say, like when you're going to play a carnival game. Well, if I played this game 100 times, this is what I should win. It tells you how much you should plan on winning, period, over the long haul. So, let's do a couple of little quick examples. Excuse me. Frog in my throat. Now, I was an artist for 20 years, and I still am a big proponent of draw what you see in probability. It's going to help you out a little bit, okay? This one's pretty straightforward, but still, I like to go ahead and draw it just so that way I have a better idea of what I'm seeing. Find the number of outcomes in the complement of the given event. So out of 231 blueberry plants, okay, let's think about that. That's my universe. That's everything I know. That's all my blueberry plants. So here they are. I've got this huge field right here of blueberry plants. So my S is equal to 231. 163 are ready for picking. So I have in here, I can say E, and there's 163 blueberries, right? But what would the complement be?
Subtracting.
Exactly. It's going to be everything out here. It's what's left. Okay. And so you come in here and just do some super simple math. Okay. You got to come here 231 minus 163. And what do we get for that? Good. Very, very good. You get 68. So the complement is out here. Okay, so my E of C is equal to 68. And remember, I told you maybe that as E of C, or muscle memory for me, whenever I took a stat class, they did it as E prime, just letting you know. So if you see that little prime for me, no, it just means the complement. Okay. I tried very, very hard to stick with the notations used in this book. That'll change it one spot, just so you know, because I have a quirk in how they wrote a formula later on. I just, as hard as I might, I just don't like the way they wrote it. And so I show you their way, then I show you my way, and I kind of go backwards and forwards with it. Let's do one more. Remember, all these notes are online, so that we can kind of still get into the next one. Determine whether the following events are mutually exclusive, choosing a diamond or black card out of a deck of cards. Okay, first off, you have to know what a deck of cards is, okay? Naively, I thought everybody knew what was in a deck of cards, okay? But to let you know now, one, go learn what's in a deck of cards. It might be a bonus question on your quiz, okay, on your final. Every semester, I do what I call a general knowledge bonus question, which is literally like, if I would have faith in humanity, I ask this question, like, well, last semester it was, can you tell time on an analog clock? Okay, not digital, analog, like what I'm wearing right now. Can you tell time on that? Only 20% of my students got it. Semester before that was, what galaxy do we live in? Okay. I was gonna ask this semester, like, what's the largest gas we breathe? But then I realized most people would get that wrong. Okay, it's not oxygen. I'll let you know now. Okay, but remember, cards now in Hawks, do you notice how this is got a little, where it says standard deck of cards? You can click that and it's gonna show you a deck of cards. So you kind of have an idea, okay? But there are two colors with cards. There is black, okay, and red. There are 4 suits, okay? There are diamonds. All right, let's do it this way, hold on. Be intentional, as I say to my intermediate algebra students. Be intentional. There are black cards. Clubs. Spades. There are red cards. Diamonds and hearts. I knew you were gonna know. And then each one of those cards, okay, has a value, and they go from ace, 1, 2, ... to 10, and then they go jack, queen, king, and they'll do that through every single one of them.
There isn't a 1, but ace is a 1.
Oh, yeah, you're right, Doug. Ace is 1, thank you. Get rid of that 1. So that's how they are. Okay, now, like I said, they'll show you that, but now knowing what you can see here, is this a mutually exclusive event? Choosing a diamond or a black card? Diamonds would be what? Okay. Can I choose a red card and a black card? No. When I pull a card, it's either going to be a red, okay, and I am using exclusive, or a black. It cannot be both, okay? There's no multicolored cards, okay? The red cards are only diamonds and hearts, okay? I challenge you to go to the dollar store today, spend the 25 cents, go get you a deck of cards, go look at them, okay? Well, how about this one? Choosing a king, knowing what you know now, or a black card. Well, let's just go back. Okay, remember that. Probability of choosing a king or black. Is that mutually exclusive? Why is it not mutually exclusive?
The king can come in all suits.
Yeah, he's in every single one of them. There are black kings, there are red kings. He's not just stuck in one color, okay? There's only 2 types of cards, red and black, 2 colors, but kings go across the gamut, so very good. So that would not be a mutually exclusive event. That would be an area where you have to say, okay, well, how many kings do I got? How many black cards do I got? Where do they match? where are they the same? And you would have to subtract that part out to get the right probability. Are you kind of getting the difference now between mutually exclusive and non-mutually exclusive? We good? Okay. Marie said that. Okay. Let's jump into order. Multiplication rules for probability. I'll be telling you a story here shortly about it. And I told you, I've said this before about this lady, and I don't think, and I'm pretty sure I did not share this as one of your discussion questions. If I did, I'm kind of glad because at least you're gonna have a better understanding of it right now. So, multiplication rules for probability before we jump into it. Let's review again, always reviewing. Okay? Especially in this class, you always want to be moving, as you move forward, always look back. There's nothing I'm gonna do in this class that you are not gonna have to reference back. Okay? Maybe chapters 1 and 2. Everything from 3 on, I'm gonna be mentioning back to 3. I'm gonna be mentioning back to 4. I'm gonna be mentioning back to 5 as we move forward, okay? So notice the addition rule. What's the operative word I'm gonna be looking for? The or, okay? Now, here's where it's going to get a little bit different, okay? With the multiplication. Remember what that or is saying. That or is saying, hey, this is a union right here, right? This and, what was that again?
Intersection.
Intersection. That's where they're the same. Can you remember that when looking at that one? Okay, now let me show you the formula for the multiplication rule. That does not mean the same thing. And I get it. Right now, that's usually when people start to hate probabilities. Okay? That right there does not mean an intersection. Okay, at all. This up here means intersection. Okay, that other and you're seeing down below. Let me tell you the best way to read this, okay, when dealing with the multiplication rule, okay? For one, in this class, how do you know you're gonna be dealing with the multiplication rule? There's no or, okay? Sometimes they're gonna use an and, sometimes not, okay? But when you read this like this, not the probability of E and F. Read it this way. The probability of E and then F. Notice how I added that and then part. That and then is going to become, you'll understand it a lot better here shortly. So let's read this as the probability of E and then F is equal to the probability of E times the probability of F. Okay? I don't want to hang on that too long, just kind of trust me on this. It all will become clear very shortly, I promise you. Independent events. When objects are placed back into consideration before performing the next stage of a multi-stage experiment, we say the experiment is performed with replacement. Now, does that mean they're always going to say the word with replacement? They will for a little bit, and then all of a sudden, they won't. Basically, what it's saying is, whatever I'm studying, if I take something out of it, I put it back in. So it's considered for the next person. Okay? Two events are independent. Okay? if one event happening does not influence the probability of the other event happening. Let me give you a good, really awesome example of this. We are looking at buying my wife a new car. So what is the probability? Okay, does this probability affect you? The probability that I buy my wife a car, does it have any influence on the probability of you passing this class? No, you'd hope to think not. Okay, and it doesn't. I'm going to buy her a certain class of car. You have no idea. You can take bets. Whether you're right or wrong, that doesn't matter whether you're going to pass this class. Those are independent events. Notice the probability here had no bearing on the probability here. Okay. He becomes a father one day. We don't know this. What's the probability? Okay, his wife is going to have a boy or a girl.
50-50.
50-50, okay? They go a long ways, they forget how horrible little kids are, and they decide they want another one. Okay? What's the probability of them having a boy or a girl?
50-50.
Very good. And unless something comes out through science, notice the odds of them having a boy or girl for their first kid had no bearing on whether they were going to have a boy or a girl for their second child. Now, like I said, unless something comes out scientifically, but right now, these are independent events. Okay, flipping a coin. Do you think that coin cares? I flip a coin, I get a heads. I'm getting ready to flip it again. Do you think that coin goes, I've given a lot of heads. I better be a tails this next time. Do you think it works that way? No, it has no bearing on it whatsoever. It's an independent event. Now, I need to say this, and I'll put it up here on the board. Mutually exclusive does not mean independent. Okay? Mutually exclusive means those events, consider where the events can happen at the same time. That has nothing to do with outcomes. Independent says consider whether one event occurring affects the probability of the other event. Does that kind of help y'all see the difference in those? Probably really good to remember that. Are there any questions? Is anybody lost right now? Because this is not the time to start getting lost. I promise you, if you have questions, please ask. Because I'm here to answer. Okay? Because good news, your midterm is probably the easiest midterm in math you're ever going to take. I promise you, I make it. It's pretty straightforward. Okay? After that, things get a little bit abstract. Okay? Not hard, just abstract. But we're going to be referencing a lot of this stuff back here a lot. Okay, so I just kind of want to make sure everybody is still walking through this. Notice we haven't done a lot of really heavy lifting in math. It's been basic, like simple fractions and calculator work, really, you know. Independent bit. Here we go. Let's do one. Okay, here's one you might have seen. Your book uses it. I'll be changing it out this year because I know eventually at some point in time, the carnival is going to come back to town. And so I'm going to take a lot of antibiotics and then I'm going to go hang out at the carnival for a day. Okay, so that we don't catch anything. I don't trust carnivals. Sorry. Okay, people want to ride those rides. Those are some pretty like dangerous rides that they're throwing up in less than like 45 minutes. Okay, just saying. Look at this. A booth at the state fair has rubber ducks floating in water. You've probably seen something like this before. For each ticket, you get 2 chances to pick a duck from those floating by. In order to win a small stuffed animal, you must pick a duck that has a star drawn on the body. If you manage to choose 2 ducks that both have stars drawn on them, you win the extra large stuffed animal, okay? After your first pick, the rubber duck is placed back in the water for your second pick. Don't hear what I just said? How does that relate back? Look, remember what I said earlier? That with replacement? Did I say the word with replacement? No, they put it back. That's the same thing as saying with replacement. With replacement, don't think of replace because you're using like your English brain, which I get it because we think in that way most of the time. With replacement means I put it back. That's how you can kind of say that, okay? Whatever I took out, which I did, I picked the duck, right? And I went, I either got it or I didn't, and then I had to put the duck back in the water. That's with replacement. They didn't say that word, but I did say it got put back in the water for your second pick. Now, if there are 50 floating ducks and 3 have stars drawn on them, what is the probability of choosing 2 ducks that both have stars on them? Now, realize we're running 2 trials. Trial 1, I'm standing at the edge. I've got my wife right here. I want to look awesome. And so I reach into the water and I grab the duck, turn around. I'm going to tell you what I got. But what are the odds of me getting a duck that has a star on it? First off, how many ducks are there? 50. So can we say for my first trial right here, we know there's 50 ducks. How many ducks have a star?
3.
Now, I'm not telling you whether I got one or not. But notice what it says. I put it back in the water. Right? Is it there? So how many ducks are in the water now? 50. So now I've got to do it again. Obviously, probably I won. Let's just say that. Let's say I got one. Yay. I do it again. How many ducks did I choose from? 50. So probably what happened was I put the duck in the water. They turned me around and then they stirred the water. Right? So that way I don't know exactly where that duck was. Well, now think to yourself, hey, how many ducks have a star on them? 3. There's still 3 because remember, I put the duck back in the water. Okay, well, this is awesome. There, I'm done. That was my second trial right there. And now we do the math. 3 times 3, remember just multiplying fractions. 3 times 3 is going to be 9. I know I'm going to have 2 zeros because of the zeros over here. 5 times 5 is 25. You can stop right there, or it's actually really kind of neat to see this one as a decimal because it lets you know, hey, what are my actual odds? Well, look here, it's 0.0036, or when you really want to get down to the nuts and bolts of it, 0.36%. That's the chance out of just 50 ducks, me getting 2 ducks that have a star on them. Okay? So now you got to think about it. And like I said, always step back and think about it. Could I do a classical probability of this? Remember, let's think about it. Classical probability says the probability of me flipping a coin is what? Classical. 50-50, right? It's 1/2, okay? But what would the experimental be? Experimental be if I did 1 trial and I get a heads, and that was my goal, was looking for a probability of heads. Well, remember, experimental says, hey, what are your odds of getting a heads? If I flip it and I get a heads, your odds are 100%. If I flip it again and I get another heads, I'm still at 100%. But if I flip it again and get a tails, well, now I'm at 66. But remember that law of large numbers? As my trials increase, what am I going to get close to? The actual probability. Notice how this one, it's got some finite things, right? There's only 3 ducks. Okay, that have a star. There's a specific number of ducks. That's a classical. You can work out some very direct numbers there. So the more I kept playing, what's going to happen? Like, is there a good probability? Could I win this? I can go up there right now today, right? Spend my $5, pick out 2 ducks and win. But what's going to happen in the long haul? It's going to be them who win. Okay, you want to see what your chances are of losing, subtract that from 1, and it's 99. It might as well be 100%. So your chance of losing this game might as well be 100% losing. So it's sometimes good to see the opposite side of that coin, hence the complement. Not what's my odds of winning, what's my odds of losing? okay? Then maybe that 0.36% doesn't make any sense, but if I said to you, I'm gonna give you two drinks, both of them look like water. In this one, you're gonna live forever. You have a 0.36% chance of living forever. Or you have a 99.7% that this is gonna kill you right now. Hopefully, most of you'd be like, I'm not taking that bet. That doesn't sound like a good bet right now, you know? So does that kind of make sense more than how the probabilities work? Well, let's change it around. Okay? That's all fine and good. Dependent events. When objects are not placed back into consideration before performing the next stage of a multi-stage experiment, we say the experiment is performed without replacement. And then two events are dependent if one event happening influences the probability of the other event happening. Okay? Do you think if I'm on a very high sugar, smoke cigarettes, drink all the time, okay? Do you think the probability of me being that type of person and then also getting cancer, do you think those two kind of play a role with each other probably? Notice how one might influence the other. Yeah, there's gonna still be some biology and stuff in there involved, but you notice how that does affect things. For our cases, we're gonna be using a lot of classical probability, but I want you to understand how this can be affected in the real world. Does it mean it's a guarantee? Is that 100%? No, I know people right now in my life that literally drink like a fish, smoke all the time, never exercise. And I know a guy like that right now, and he's 97 years old. And he's been that way his whole life. But then you can turn the story. We all know people that died really, really abnormally young from doing the same thing. And then people just die for other reasons. But sometimes that correlation is right there. Okay, so kind of think of it that way. Let's go back now to the carnival. Consider the rubber duck again, okay? So the guy says, hey, you know what? I am getting really tired of having to stir this water every single time I do this. I'm getting wet, my shoes are wet. Tell you what, how about whenever you pick the duck, you just hold on to it? Don't you think that makes things better for you? If you get to hold on to it? Don't think so? Or do you know? Let's look at it. Gotta know. I saw a yes. You're choosing two ducks still. In trial one, how many ducks do I have to choose from? Trial one. I just paid my money. Here we go. Let's try again. How many ducks? 50. How many ducks have a star? 3, exactly. So the probability of getting a duck on my first trial is 3 out of 50. Now I gotta go again. So here's my second trial. Put this down. We know we're gonna be multiplying.
249.
What'd you get?
249.
249. Why is that?
Because you got a star already, and you put it back, and then you only have 49 ducks in the bowl.
Very good. Did you hear what she said? I picked a duck out. First off, can we all agree I have changed the amount in my universe? There's no longer 50 ducks in the pond anymore. There's now just 49. I did not put it back in. I'm holding on to it. Is my duck. Okay, so now there's only 49. If I got a duck and it had a star, how many are left floating? 2. That's how come this turns into 2 out of 49. You kind of seeing it? This is sometimes where people start getting lost a little bit. Okay, remember your denominator is the number of things in your sample space. That's everything. Okay, the numerator is the subset. What am I looking for? What is the frequency of the thing I'm looking for? Okay, so whenever you take something out, you have changed the size of your universe in your second go around. Okay, and so now we can go ahead and do the math of this very quickly. Come in here, 3 times 2 is going to be 6. 50 times 49. You end up getting 2,450. Doing the quick math to that, you get 0.0024 or 0.24%. Notice you actually have less of a chance now. Why? Because what?
Signs changed.
Oh, yeah, but still, why though? Give me a reason why is it less now? Why do I have less of a chance?
You didn't put the third star back in, so you're lessening your chance every time you take one out.
Exactly. Did you hear what she said? Very good. You've moved things. Remember in the last example, I pulled one out. I look at it, yay, I got it. I put it back in. I still have 3 of them in there floating around. So it helps me. But the moment I take one out and hold it, now you've only got 2 out of 49. And really, to be honest, 2 out of 49 there might as well not be any change at all. But you did change things a little bit, which is why it dropped your percent chance of winning by just a little bit. But now it's even less. I mean, let's face it. Now you've got like a 99.75% chance of losing. Okay? Really in the scheme of things, when something is that much of a percent, you might as well just consider yourself losing. Okay? But we're dealing with probabilities. Always want you to remember that, even when you leave this class. Probabilities are never, ever, ever conceptual probabilities like this one, 100%. Okay? But they can be so close, they might as well be. So, conditional probabilities. Okay, this is where the notation is going to get weird, but you literally just did a conditional probability. Okay, conditional probabilities are denoted the probability of f, that little straight line. Okay, given e. What it's saying is, what is the probability of f given that e has already happened? What is the probability of me drawing a duck on my second term, my second trial, given E, my first trial, I grabbed a duck, I got it, and I held it out, has already happened. Notice because E has happened, what's happened to that second trial? It has affected things, okay? It's no longer 3 over 50 times 3 over 50. We're now looking at things differently. Conditional probability says something has affected things, okay? For 2 dependent events, E and F, the probability that E and F occur is given by the following formula. The probability of E and F, is that a intersection, that and? Remember, I told you, don't read it that way. Read that probability of E and then F. Okay, I get it, because if you think back to your addition rule, you had that and built in there. That one was an intersection. This one is not. This is saying and then. Okay. You just did this. Okay. Think of the ducks. The probability of E was what? The first round. How many ducks did I have?
30.
Exactly. I had 50. How many ducks had a star? 3. Okay, well, how about this? The probability of F, given that E has already happened, and we know these are dependent events because the first trial is affecting the probability of the second trial. So what is the probability of the second go around? You said it perfectly. What was it? Over. Very good. 2 over 49. That's what this one's saying right here. This one times this one. That's literally what it's saying. E happened first, and then F had to happen. Or in some cases, they may say F happened first, and then it affected E. Okay? Good to note. Let's look at one. What is the probability of choosing two aces in a row from a deck of 52 cards. Assume that there are 4 aces in a standard deck and the cards are chosen, operative word, without replacement. That means I'm not putting it back in. So just going on what you know, is that going to affect probabilities moving forward? My first probability, first off, how many cards in a deck? 52. When in doubt, there's 13 decks of each suit. 13 times 4 gives you 2. So I know trial 1, my P of E, okay, or we can say it this way, the probability of drawing that first ace. Well, I know how many aces are there? 4 out of 52. But now, does that probability affect the next round? Yes, because I'm not putting the ace back in. If I was, then it wouldn't matter. Just go ahead and just do it again, okay? Because I put the ace back in, we don't know. So now the probability of F given E has already happened. That's going to be the probability of drawing that second ace. Well, if there's 4 aces, I took 1 out. How many's left? 3, exactly. That's the frequency of the thing I'm looking for, okay? Now, how many cards are left in the deck? Huh?
51.
51, exactly. And then we just do some math, right? Come in here, and we know all this is going to equal 4 over 52 times 3 over 51. Ends up being 12 all over 2,652. Or that really, and the reason I do like turning these into decimals a lot, one, man, I don't have to worry about trying to simplify a fraction. But 2, I understand percents better than I understand fractions. Okay, because what this is telling you right now as a fraction, okay, your odds are 12 out of 2,652. Well, I don't know about you, that doesn't make a lot of sense. But I do know that 0.0045 makes a lot more sense, especially whenever I turn that into 0.45%. So basically, what are your odds of drawing 2 aces in a row from a deck of 52? Not great. Once again, I will say this though, you have a better chance of drawing 2 aces in a row than you do of getting rubber duckies in a pond. Not much. Does that mean impossible? No, it does not mean impossible. Does it mean improbable? Yeah, impossible is different than improbable, okay? So no, we are going to be very, very close, but still our closest is toward the losing end of that. So depends on how you decide to take the bet. And I will show you that when we start doing expected value stuff, it's going to actually surprise you how much you would have to bet for this to be a winning probability for you. There is an amount of money that you could actually put down on this to say, this is a winning bet for me. Like if someone said, hey man, do you want to take a bet that you can draw 2 aces? And I'd have to go, hold on. I'm going to listen to my stat teacher and I'm going to go do the math. Yeah, I'll bet you like $3 million. And that's a break even at 3 million. That means get playing the game long enough, your break even is going to be 3 million. To actually be winning, you'd have to play a bit more than that. Okay. Good so far? Are we good so far? Honestly, I don't want to jump ahead. Okay. Do you realize that these are just numbers? That probability of E, while its notation looks really, really weird, it's still a number, correct? It's still technically a variable. If you want to kind of just make it, let's go back to college algebra. It's a variable. If I put X there and I put a Y there, can you solve for those? Right? Can you do some algebraic manipulation and kind of move stuff around if you need to? Hope so. I mean, to be in this class, you kind of got to be able to, let's be honest, okay? I'm saying that because notice, I have a probability, let's just worry about the top one, okay? I had the probability of E and F is equal to the probability of E times the probability of F given E. But what if they gave me the probability of F given E? And what if they gave me the probability of E and then F? But they didn't give me the probability of E. Could I solve for it? Can I just move stuff around? Yeah. Think about what the other thing said, okay? We can shove stuff around wherever we want. Notice this says this, hey, if I have the probability of F given E, think back to what your formula says. Oh, let me erase this. I'm actually about to recopy that. Apologize. Remember, your original formula said this. The probability of E and then F, if you read it that way, you won't get confused thinking intersection, okay? And then F is equal to the probability of E times the probability of F, given that E has already occurred. If you kind of just say that as a whole sentence, it does make things a little bit easier. But notice all they did was algebra. They said, hey, let's just come in here and multiply both sides by the probability of E. What happens there? Those reduce out, right? And then we're given this formula right there. Okay. And that's how that works. Good so far? Okay. That is the conditional probability. Now let me move on to the counting principle in our last little few minutes. I'm gonna go through this pretty quickly, but it is kind of, it's a fun thing. And it leads into chapter 4.4, super easy. So theorem, fundamental counting principle. For a multi-stage experiment with n stages, okay? Things happen. Flipping a coin, how many stages is there? There's 2 in there, right? Heads or tails, okay? Where the first stage has K1 outcomes, the second stage has K2 outcomes, and the third stage has K3 outcomes, and so forth. The total number of possible outcomes for the sequences of stages that make up the multi-stage experiment are K1, and you can see the formula there. It's literally just saying, like saying I'm flipping a coin. How many things do I have to multiply together in the first stage? Just 2, right? Well, if I ran another one, how about times 2 again? If I run another one, how about times 2 again? Okay, that's all it's saying. But now in the real world, things don't work that way. So look at it this way. Kilby begins her first year in an online degree program in July. The first semester, she will randomly be assigned to one section for each of the 4 different core courses. If there are 8 English 1 sections, 12 college algebra sections, 11 American history sections, and 5 physical science sections, how many different options are there for Kelly's schedule? They're basically saying this. Let's just say it didn't matter. You don't care. You just tell your advisor, just put me in some classes. Timing doesn't matter. How many different ways could your schedule be? Is what it's saying. It's like all the possible outcomes. Okay. In this one, I think of it like filling in the blocks. I've got some blanks here. I've got a blank here times a blank here times a blank here times a blank there. Well, think about it. There's 8 English sections, 12 college algebra sections, 11 history sections, and then 5 physical science sections. When you do this, you get 5,280 different possible schedules you could possibly have. Well, that's a lot. Let me show you why this works. Here you are. You just walked in. How many choices do you have of an English class? 8, right? So you choose it. 1, 2, 3, 4, 5, 6, 7, 8. And then there are 12 different college algebra classes you can take. So let's say you get this one. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then you get this one here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You notice how this is working out now? Doesn't it look a lot like your tree diagram whenever we first started learning about probabilities? It's working exactly the same, except now instead of just being 2, 2, 2, 2, this is gonna say, hey, your first choice, you have this many options. Your second choice, you have this many options. So once you just multiply those together. Your third choice, you have this many options, multiply that to that number. And that's exactly how that's working. That's how come at the very, if you decided to draw this out, you would end up having 5,280 different ways to pick that schedule. So you could take like a morning class, or say a morning, 9:30. Notice how that could kind of work. That's how that kind of works out. Another way to think with those, we do it this way. Same thing, but let's do it this way. The governing board of a local charity, Mission Statesville, is electing a new vice president and a secretary to replace the outgoing board members. If the board consists of 11 members who don't already hold an office, okay, that means there's probably like a president out there, but he's already got an office, you can't even count him. He's sitting over here doing his thing. How many different ways can 2 positions be filled if no one may hold more than one office? Well, let's think about it. We've already got a president, so we don't think about him. He's not even counted, so don't even think about him. But we do need a what? A vice president. How many people do I have to choose from for vice president? 11. Yeah, I have 11 people. Sweet. Okay. I randomly choose one of you, you become my vice president. Boom, I picked you out. Now, how many people do I have to choose from? 4 secretary. So notice, for secretary, I only have 10 people now, because one person has been removed from the running. So all the possible combinations I could probably have would be 11 times 10. And that's just equal to 110. This is what it's saying. You're gonna be VP, she's gonna be secretary. Or you could be VP, he's gonna be secretary. Or you could be VP, and notice all those different possible, or I could say, you're gonna be VP, and then it just kind of keeps going through. Notice that little tree kind of starts spreading out from there. But instead of using the tree, we can just go, let's just multiply those together and get all the possible combinations. That's exactly how, and you'll find this out in the next section, it's exactly how passwords work. How many possible combinations are of a 5-word password or a 5-letter password? Well, think about it. How many words how many letters in the English language? 26, right? Well, it'd be 26 times 26 times 26 times 26 times 26. That's all the possible combinations you could ever have. Which for a human trying to figure that out is, for a computer, seconds. But still, that's why they start telling you, that's how come they're always, say how your what do you call it, passwords have gotten worse and worse and worse. They're like, hey, now we need, you need to do 12 letters, 4 characters, your firstborn, and then, all this other stuff, because these passwords are just getting broke so fast now. That's why. Let's do one more. It's gonna be a phone for me and her, because she's gonna understand, and probably like 3 other cool people in this room. The rest of you probably suck. There's a wonderful game. I'm gonna skip this one. There's a wonderful game that we play at my house called Clue. Does anybody know the game called Clue? The board game. Awesome. Remember Clue? Used to be a movie in the 80s. Don't go watch it. Haven't watched it, but I'm worried about movies from the 80s because you never know how much nudity's in them. I watched them all on TV, so I don't want to start telling you now, hey, go watch this movie. I watch them now on like Amazon. I'm like, holy, there were so many naked people in this movie. So I'm not gonna tell you ever to go watch a movie like that. But Clue is a board game in which you must deduce 3 details surrounding a murder. In the original game of Clue, which yes, we just played this weekend. Okay, the guilty person can be chosen from 6 people, and there are 6 different possible weapons and 9 possible rooms. Like Colonel Mustard, okay, killed, I forget the other person, killed the butler in the bathroom with a wrench. Okay, or you could possibly be the murderer. You wouldn't even know it until you get done with the game. You're like, oh, I'm the murderer. Okay. So at one point in the game, you've narrowed down the possibilities, okay, to 3 people. Okay, there's 3 choices right there, right? 4 weapons and 7 rooms. What is the probability of making a random guess of the person, murder weapon, and location from your narrowed down choices and the guess being correct? Well, think about it. How many correct choices are there? Just one, right? There's only one way to get this correct. But now let's look at all the possible ways. How many people have we narrowed it down to? 3. How many weapons? 4. How many rooms? 7, exactly. When you do the math of this, okay, you end up getting 1/84 or 0.1190. Basically 11.90%. So you still only have an 11% chance. Now, to be honest, okay, if you do it like right at the beginning of the game, we figured out the odds on that in the last class, and I think you'd have to do it, but it would literally just be, you just start the game, you're like, I'm gonna make a guess right now. I don't even know, I haven't done anything, I haven't rolled any dice yet. I'm gonna guess right now. You'd end up having to do the 6 times 6 times 9 and divide that by 1 divided by that number. So if you ever play the game, there you go. Good thing is in the game, you actually have to start narrowing down things and there's ways to do it, but it's actually a very, very fun game. So how do we feel about addition property? What's the operative word we're looking for? Or, okay? With the P of E and F, we don't think of it as intersection, do we? We think of it as what? P and then F. Okay, perfect. Okay. So this leads us perfectly into 4-4. I will see y'all next class. Have a wonderful, wonderful weekend. I will email you about whether we're gonna have class or not on Tuesday. Regardless of whether we're gonna have it, I will email you.